Hi everyone. Today we are going to discuss about CAP theorem. It is a very useful in the IT industry. So please understand this theorem very carefully and try to implement it in your systems. So in this video we will understand CAP theorem with real world examples and clear diagrams. So everyone knows CAP means consistency, availability, and partition tolerance. So it comes in distributed systems mainly. So we can go to this in detail. Why do we need CAP theorem? So modern systems are distributed. You know that our application is not running on a single server. It is running on multiple servers located in multiple places, multiple regions, multiple countries. So it is distributed across the world. It's not like a single machine is uh, delivering your websites or your applications. It is not like that. There are multiple servers and multiple uh, regions. So it is distributed, and we cannot make sure network is always available or it should be always running. It will never fail. That is not at all possible, right? Network failures are inevitable. It can happen at any time. So we need to understand system behavior during failures. So anyway, network failures are inevitable. So we have to decide how the system will behave during these failures. That is CAP or CAP theorem. So what is a distributed system? We have multiple nodes. Data is shared across the nodes, communicate over network. Example, microservices, database, cloud apps. In a real world, almost every application is running on distributed system. Okay. So here you can see two images. One is a normal scenario, client communicating to nodes. All nodes communication is happening, nothing is failing here. You will get consistent data, system is available because nothing is failed here, everything is available. It's a very happy flow. The second state, you can see communication between node A and B is not happening, it is failed. So a partition occurs, nodes cannot communicate, so communication between the nodes are failed. So this is a success scenario and failure scenario in a distributed system. So the theorem, CAP theorem definition is a distributed system can guarantee only two of the following three properties at the same time. Okay, two means you have to choose like this, CP or AP. You cannot, other options are not available. Like you cannot say like CA, either CP or AP. You have to, P is always there. So you have to choose from C or A. Means consistency or availability. This is CAP theorem. So what is consistency? Consistency is about correctness. Means every read gets the latest write. Okay, all nodes see the same data. For example, bank account balance or payment systems, it should give the exact value, right? Exact and correct value. So consistency guarantees that you will get correct and latest data. That's what consistency guarantees. So you can see node A, B, C. So every node is having the same value. So from which node you are reading doesn't matter, you will get the same value. Okay, so it is structured in such a way so that you will get always correct value. Availability means is about always responding. Okay, means it should respond always. So here every request you will get a response, but no guarantee that data is latest. It may be a stale data, it may be previous data. There is no guarantee that data is latest. So here we can, in social media feeds or product recommendations in the Amazon, Flipkart or any other site, they can use this kind of approach, because even if you are getting stale data or data is not latest, still you will get something. That is the idea. So there is no guarantee that data is latest, but still you will get a response always. That is availability, means always available. So every request gets a response. Data may be stale. So in the diagram also you can see the client can communicate node A, B or C. Means if B fails, still it will get data from A. If C fails, still it will get data from B. Like that it works. So this is availability. Consistency is if fail, don't give wrong data instead of fail. But availability means is fine. If the data is not latest, still it is fine, always be available. So partition tolerance is the next in CAP. System is still running, means system works despite of network failure, and nodes may not communicate. So node A to B communication may not be happening, but system will be running. If one node fails, means doesn't means that the entire system is down. One or two node can go down, or communication between one node to another node may not be happening. Still the system will be running. So reality check, network failures are unavoidable, hence P is mandatory. So P will happen, that no one can avoid it. It happens because of many infra related issues or network issues, internet issues. So P is always mandatory, we cannot avoid. That is about partition tolerance. So the real CAP choice. Okay, when a partition occurs, you must choose between consistency or availability. So it's based on your choice. You can based on your use case, because for a bank application or something like stock market, you have to choose consistency. Availability means for social media applications, the comments or the latest feeds, you can use availability, because even if it is a stale data, or if the data is not that latest, still it is fine. CP system consistency plus partition tolerance. CP system prefer to fail rather than return wrong data. Okay, CP system prefer to fail rather than return wrong data. So it may reject requests, but it guarantees correct data. For example, banking, Zookeeper, HBase, MongoDB, these kind of applications is consistent. They prefer to be consistent rather than return wrong data. So this is in the diagram you can see consistency over availability. It's a CP system. So request is failed, that's all. It will not give any stale data or old data. If it is not there, means if there is some failure, means partition tolerance means it prefer to fail rather than giving wrong data. AP system, is availability plus partition tolerance. AP system prefer stale data or downtime. Be available always. Okay. So behavior is always response. Data may be stale, eventually consistent, because whenever that failure we corrects, then the data will become consistent. But during the downtime, data may be stale. So that is not very frequently happening, right? Sometimes some downtime will be there, something may fail. So that time you will get stale data, but still that time also system will be available. But once that issue resolves means you will get consistent data. There is no issues. So for example, Cassandra, DynamoDB, CouchDB, social media applications, these kind of things will want to be available always. For example, some other applications, news applications and all, the latest news will be there, but sometimes if this availability some partition tolerance happens means it can show the previous newses. Latest news may not be available, but still you can watch newses maybe 2 minutes before, 5 minutes before newses will be available, right? So that is one real world example. So availability is depends on your application's use case. You can choose either availability or consistency. So CPU versus API, I almost covered everything before, but here is a comparison. Availability, CP consistency may fail, but AP always available. Consistency, CP is strong, but AP is eventual. Means during downtime it may not be consistent. That is what eventual means. Okay. Use case, consistency in banking and availability in social media apps. So some more real world examples here. Banking application. Banking application is a CP system, consistency. So account balance update, network partition occurs, choice, it reject transaction, avoid incorrect balance. Okay. Scenario is one account balance update is happening. During that time, some network partition occur. So it will choose reject transaction so that this incorrect balance you can avoid. It's a real world scenario. So AP system, for example, Instagram likes. So scenario, like count differs across servers. Sync happens later. Always show something, count may differ briefly. So your like count will be there in multiple servers, but all servers may be having slight differences. Syncing between servers happening may be not frequently, maybe it may take some time. So during that time also you can see something. It may be slightly different count. Okay, so still that is fine. It is not a big deal, right? So this is a real world example of AP system. So the common myth in CAP is you can only choose two of C, A, P. In reality, when partition occurs, choose C or A. P is always there. You cannot avoid P. So in modern architecture, how companies design systems. CP for critical data, AP for non-critical data. So you can mix based on business needs. For example, order placement, CP, recommendations, AP. So in a single application, you can have both CP and AP for different features. So CAP theorem in microservices. Service to service calls, network latency and failures, design decisions matter. Okay. In microservices, we will be calling sometimes we will call another service from one service, right? So service to service calls will be there. So in these scenarios we can choose consistency or availability based on our services. And in network latency and failures also we can decide C or A. So these all are about our design decisions and our feature and our how important this service and everything. So in summary, CAP theorem is about trade-offs, not limitations. CAP applies only during partitions. Partition tolerance is unavoidable. Choose consistency or availability based on use case. So this partition happens occasionally, it is not very frequently. So that time how the system should behave, that is what CAP theorem. It's not like every time uh, the consistency or availability only it will be there. Every time the data may not be consistent. It's not like that. If the system during the partition failures or the partition, the system that time how the system should behave. That is about CAP theorem. Okay, that's all about this CAP theorem. If you like this video, please subscribe and share. Okay, thank you so much.